Good morning, Astronomy 1010. Welcome to Lecture 4, Part 2. Today we're going to clean up the history of astronomy, do a little smidgen on Galileo, and then transition into Chapter 4, which is all things Sir Isaac Newton, forces, motion, gravity, other stuff we need to understand the motions of planets in our solar system. Last time we finished up with Kepler's 3 laws of planetary motion. Those are kind of a big deal in our class because they teach us how planets orbit the sun. The fact that their orbits are not perfect circles is very important. It means that they get further and closer to the sun at different times of the year. Where's my history lesson here? And Kepler, Johannes Kepler, laid out his 3 laws of planetary motion in a legendary book called Harmonices Mundi, on the harmony of the worlds. He proposed that a planet orbits the sun not on a circular orbit, but on an elliptical orbit, with the sun located at one of the focus points. The significance of a focus point is that it helps to sort of define the properties of the ellipse. We sort of learned a little bit about that in our lab last time. He also discovered that not only do they orbit on ellipses, but that planets sweep out equal units of area in equal intervals of time. And if you look at the animation here, you can see it's not a very good animation, but the planet tends to kind of speed up when it gets closer to perihelion, and it travels at a slower speed farther from the sun near aphelion. And what's preserved is the amount of area that's being swept out by the planet. His 3rd law, which is going to be the most useful to you, is a relationship between the period of a planet, the sidereal period, by the way, and its semi-major axis, which is kind of like the average distance between the planet and the sun. We made a model of an ellipse in our labs last time, but because these are testable issues, I thought we could just take a quick moment to make a cheap model of an ellipse, just to label some parameters. By the way, I should make mention that this is our last class before we go in person, which will be next Monday, correct, students? Are we ready for that? I think I am. In any case, I wanted to let especially any students in the night class know that I did successfully get our night class moved to room 6062, which is what I was hoping for. So Astronomy 1010 section 101, we're going to meet Monday in room 6062 at 6 p.m. Whether or not we have office hours will actually depend upon what happens today. I'm deciding what to do about homework at the very end of our lecture today. So the daytime students, do we remember what class, what our room is? I think I went over that last time. I figured I'd just mention this at the beginning of lecture when people are most likely to watch. Does anyone know their room here? I'm looking it up.
Yeah, I believe it's 6062. And
okay,
then
same one.
2050.
That's great. Yep, 6062. Yeah, the lab room is on the 2nd floor, but once we meet up, I can kind of tell you. So I will see you daytimers, section 001 and 002. Both of you meet for the same lecture, Mondays in room 6062. Okay, cool. Anyways, let's make a model of an ellipse, one that we can use just to sort of define some parameters. I'm going to leave myself a little headroom and make a line that's maybe, I don't know, 10 centimeters or something like that. I guess I'll make 50. And mark the midpoint of that line And then just draw another line that's kind of perpendicular to it. But make sure that line is a bit shorter. And then what you want to do is kind of connect the edges. Into a kind of football shape. Okay, so it's a bit of a cheat for an ellipse, but we're going to go with it. And then we should have focus points equidistant from the center. The focus points define the ellipse. Focus point 1, focus point 2. This, of course, is the major axis. We can label just like we did during our lab. This is the minor axis. We can label the distance from the center to F2 x, and we can label the distance from the center to the edge as a. Okay, where x is called the focus offset or the focus distance. I'll go with focus offset. It's how far the focus points are from the center of the ellipse. A, of course, is the semi-major axis, which is half of the major axis. But also, we should note in parentheses, it is the average distance from the sun to a planet that orbits on such an ellipse. Put that in parentheses. The most important property of the ellipse is called the eccentricity. Which gets the symbol E, lowercase e. And you can calculate it by doing x divided by a. And the eccentricity basically means percent squishiness of the ellipse. So the domain of E is greater than or equal to 0, but always less than 1. If you actually get to 1, an eccentricity of 1, I think, changes your geometry from an ellipse to a parabola, I believe. Make a note that if your eccentricity is 0, that's a perfect circle. An eccentricity of 0.5 is an egg, and an eccentricity of 0.9 is a cigar. So that's a little rule of thumb right there that prevents me from having to try to draw that. Another thing that I thought we could include is the eccentricities of a few planets in our solar system, and a pretty good range would be to do Venus, Earth, and Mars. The eccentricity of Venus is 0.07. Sorry, 0.007. I'm not even. which is so close to zero that it's pretty much a circle. Even Earth's eccentricity at 2%, 0.02, is very circular. Mars is only slightly deviating from circularity at 9% squishy. I think one of the, okay, so the highest eccentricities in our solar system are Mercury and Venus and Pluto. I actually should have included Mercury in this. Okay, Mercury comes before Venus, but if you can forgive me for that, presuming you know the order of the planets, Mercury's, I believe, is 21%, which is very extreme for a solar system planet. Actually, this does make a kind of sense because I've ranked them in order of circularity, right? So I still have some logic to my method here. So this is circular to more eccentric. One could forgive the ancient Greeks for thinking that the planets orbited on perfect circles. You know, if you take a look at a ellipse that's 2% squishy, your eye can really not distinguish that from a perfect circle. Look at this, which I showed you this thing last time. But if I type eccentricity into Google here, this cartoon image shows you what some eccentricities look like. Ooh, it's better. Google makes it harder now to. Yeah. There we go. You guys will notice that even if your eccentricity is 0.2, 20%, which is like Mercury's, notice that the orange ellipse looks very much like a circle to the naked eye. Only around 50% do you really start to notice that you have an oval or an egg shape. And you can see above 50%, it starts to really get elliptical, shall we say. Usually things like comets have orbits like this, right? But planets, planetary orbits tend to become circularized. And that's because of the way in which our solar system formed. And that's something we'll learn about later on in this class. The formation of our solar system was a very violent place with many planetesimals and sort of meteoroids slamming together in this violent collisions. Multiple collisions as you spin around in a disk tend to circularize your orbits because they sort of enhance the collisional directions in the forward sense, but they tend to cancel each other out in the side-to-side sense. So between collisions and gravitational nudges, planets over time get circularized orbits. Things like comets can have very eccentric orbits, and they plunge in and out of our solar system, just like Halley's Comet, which we studied. Okay, so you already kind of did this in your lab, but I thought having that in your notes, I probably will test you on this. No tricks, okay? So I expect you to kind of know a little bit about ellipses. I'm ready to move on if you guys are. Can I erase that? Then I will do so. Okay, let's learn a little bit about Galileo. Galileo lived for almost the exact same span of time that Johannes Kepler did. They were contemporaries. Whereas Kepler was an astronomer working in Germany, let's look at the dates here. The life of Galileo spans from 1560 to 1640, roughly. And if you look at Kepler, it's 1570 to 1630. So Galileo is born 10 years before Kepler and dies 10 years after. They basically occupy the exact same span of time. I'm not a historian, but this is kind of somewhere between the Renaissance, which was Copernicus, and the Enlightenment, which was Isaac Newton. And during this critical time in the history of science, not only was astronomy being developed, but people were starting to really understand what science is and what science should be and how it could be done right. In particular, Francis Bacon's publication of his scientific method was really inspired by the things that Kepler were doing and Galileo were doing and the places where they got it right. So let's talk about what makes Galileo so important for us to learn about in the history of astronomy, and what he did deeply influenced the work that we're going to do this week and next week regarding Isaac Newton. So Galileo Galilei was a famous Italian physicist and an astronomer. These were two important fields he made contributions to. And people refer to him as the father of experimental science, because he was one of the first people to actually conduct what would seem like modern day scientific experiments, where he tested hypotheses and he built machines to investigate the secrets of nature. He, for reasons that we will explain later, was an extremely strong advocate for the Copernican model of the solar system. And this eventually got him into some hot water with the Holy Roman Church. When I think of Galileo, I think 1600s, that's sort of my, not that I'm going to test you on dates because I'm bad at that myself. He did some experiments in physics. One that we would like to focus on in a little bit later on is he built an inclined plane to prove all objects accelerate toward Earth the same, regardless of mass. He is credited with discovering something called the local acceleration of Earth's gravity, which we will call little g, as all physicists do. I'll talk about that in a little bit. One of the legends about Galileo goes that when he was a young man, he deduced a very important property about the period of pendulums. This is a classic problem one must study as a physics student. You calculate the oscillating period of a pendulum. Radical, and Josh has studied some physics, so he understands it's like radical G over L or whatever it is. He deduced that when he was like 16 years old by studying the oscillation period of a chandelier using his pulse as a timing device. So he sat in a chair using his heartbeat and the pulse on his wrist. He measured the period of an oscillating pendulum. Very cool. That's the kind of thing that Galileo was famous for doing. Now, Galileo did not invent the telescope. That was credited to Hans Lippershey. He was a Swiss lens maker. Hans Lippershey invented the telescope and wrote Galileo a letter because he was a famous scientist and said, hey, dude, I just discovered that if you take some pieces of glass and you grind them in this shape and you put them in a tube together, you can like see things that are far away. You can magnify things. By the way, to magnify something with a telescope is actually to change its angular size, okay? We'll learn about that a little bit later, but most people, when they look through a telescope, they think it makes it closer. And certainly that's how it feels, right? But what's happening is you're taking something that looks this big in angle, and now you're making it seem that big in angle, right? So it seems like it's getting closer. That's certainly what I'm doing to create the illusion, but it's actually angle that's being changed. You don't actually make the distance to the planet closer. Everyone does at least understand that, right? Okay, so he built the first astronomical telescope. Oh, sorry, he built the first telescope, but what Hans Lippershey didn't do and what Galileo did do is he took it and he started looking at stuff in space with it. So whatever, I don't know how the letter would have gone, but it would have said, hey, I invented this thing and you can peep into your neighbor's windows with it. That's pretty cool, right, Galileo? And then Galileo said, I'm lying, of course. And then Galileo said, well, I've got a better idea. Let's turn our peeping skyward and let's uncover the secrets of nature. So we say that Galileo built the first telescope for astronomical use. And using his telescope, he made a number of key telescopic observations, which I would like to list for you. Actually, maybe I could put them all down here and then I could walk you through with a slideshow. I think that might be more meaningful. So his key telescopic observations were craters on the moon. And I'll show you slides for this in a minute, but let's get them in our notes here. Craters on the moon, stars in the Milky Way, the moons of Jupiter, now called the Galilean moons. He observed the rings of Saturn. He observed, let's see here, sunspots. And lastly, but not leastly, the phases of Venus. So those are some of his key telescopic observations. And I'd like to walk through each one of these in my slideshow to help you understand why they were all important for him to confirm the Copernican heliocentric theory. One last thing that I'd like to put in your notes, I'm gonna just try to squish this in if you don't mind. He also wrote a book, and the book is called The Dialogue Concerning the Two Chief World Systems. If you guys can see and read that. It was sort of a play about heliocentrism versus geocentrism. I think I have a copy of it somewhere here on my bookshelf, but I don't want to waste time rummaging around for it. Okay, so I figured I'd kind of do all the notes in one little section here. And now maybe we can sort of discuss Galileo's observations, and you guys can see if you can understand, or if you guys can reach some of the same conclusions that Galileo did based on your knowledge of the Ptolemaic solar system. Okay, imperfections on the moon. The easiest thing to look at with a telescope is the moon. And by easy, if you ever have taken a telescope and tried to point it at the moon, you might discover that that's also a little bit difficult. The moon is easy to see with your naked eye, but A telescope looks at a very small area of the sky, an angular area, so you have to kind of wiggle it around to get it in there. When you do, even a small telescope reveals a whole network of craters, thousands upon thousands of them. Now, we're going to study the moon later, but these areas here, they're craters. This stuff, these large gray spotches, are what are called maria, which is Latin for seas. They're not actually seas, they're volcanic rock, and I'll teach you about their meaning and origin later. But there are maria, there are craters, and the cratered area are called highlands, okay? Does anyone know why craters would be troubling to a Ptolemaic or even a Platonic version of the solar system? What did Plato believe about planetary bodies that this would seem to contradict?
They were absolutely perfect.
Yeah. This looks like the messed up, corruptible world of Earth, where there are mountains and landslides and, all kinds of messed up terrain. This did not look like the perfect geometry that Plato had imagined. So this would have been a threat to the geocentric Platonic solar system. Okay, the Milky Way is a band of light that you can see from a dark sky. Forget about trying to see it from Providence or Warwick. But if you're out in Block Island or maybe even somewhere in South County along the shore, you can look up at night and you can see a cloud and then realize, wait a minute, that's not a cloud. That's like up in space there. And it's a band of light. If you have a camera, long exposure photography will even reveal the dust lanes, which block much of the starlight from our galaxy. Got to take my 1020 class to learn about that, right, Josh? Okay, anyways, people must have seen the Milky Way because all you have to do is look up and see it in a dark sky. But they wouldn't have understood that it was either in space, or if they did understand it was in space, it might have been thought of something that might have been painted onto the crystalline sphere. When Galileo observed patches of fuzzy light with his telescope, he was able to resolve it into a myriad of thousands of stars. And he's no dummy, right? That means that the stars lie at a variety of different distances. But let's take ourselves back for a moment to the Aristotelian, Ptolemaic, Platonic, geocentric solar system. The stars were also all supposed to be stuck to a fixed sphere at the edge of the universe, right? So if suddenly stars are lying at a variety of different distances, you basically just blew the whole lid off the Platonic solar system, and suddenly there's these big gulfs of space between the stars. And that would have probably been terrifying or awe-inspiring to a Galileo observing it for the first time. Next, he discovered, when he looked at Jupiter, that Jupiter, he probably couldn't see this. By the way, this is very similar to what it looks like through our telescope. And we observed it last year. Josh, you got to see it, right?
Yeah, we saw all four moons. Like it was like, here's Jupiter and here's the moons on the side of it. It was pretty cool.
Yeah, they're actually pretty carefully aligned with the stripes. I don't know who took this picture, but I have a picture that one of my former students, Chris Gilbert, took. I wonder how hard it would be to find that for you guys on short notice here. I think pics, I might have put them in here, 16-inch images. Yeah. So this is actually taken from our telescope by one of my students. So this will seem very familiar to Josh. Let me see if I can zoom in on this here. So you can see Jupiter as a small disk, and you can actually see the stripes of its ammonia cloud tops, right? And then in a row, you see 1, 2, 3, 4. They look like little stars in the telescope, but they're actually the largest moons of Jupiter. Galileo named them the Medicean stars after the Medici family, who were wealthy merchants and funded some of Galileo's astronomy projects. But the funny thing is, though he might have tried to call them Medicean stars, eventually they became known as the Galilean moons. Don't let your patrons know this, okay? It might. Anyways, If you look at the lecture, oh, sorry, not the lecture notes, but if you look at the notes that Galileo left in his research logs, where am I here? I'm stumbling over my words. Galileo left behind some notes of his telescopic observations. And on 79, function F5, 79, here we can see Galileo noticing that night after night, the moons, and you can see this too, Josh has been out at least twice, I think, to the telescope, maybe more. So Josh, you might have actually seen them yourself shift their position back and forth in front of Jupiter, right?
There was like one night we only saw 3 moons because it was like one was behind Jupiter or something. It was pretty
Yeah.
cool.
Yeah, sometimes I've even had a public open night where I started off and one was behind Jupiter, and then it'll pop out at some point, like a fourth one will be there. So the period, I think, of EO is 40 hours or so. So in a 4-hour public open night, you're doing about 1/10 of its orbit, right? So, you know, it's possible to see it move significantly even during a single observation session. Does anyone, I mean, this should be obvious, but why does this challenge the geocentric solar system? Would that, anyone want to guess why Galileo seeing this would further enhance his belief that the sun was the center of the solar system? Is that an obvious leap or is that a not obvious leap, friends?
Because the moons are orbiting around something that's not Earth.
Exactly, Marissa. Beautiful. And it's not a hard leap to say, well, these moons are like the whole thing behind the geocentric solar system is everything needs to be orbiting around Earth, right? Like Earth is the center of the whole universe, and some kind of magic about the center of Earth is this absolute state of rest, and everything has to be orbiting around there. If you could see moons going around Jupiter, it's not hard to believe that Earth doesn't have to be the center of the damn cosmos or the center of every orbit. The next thing he did is he looked at Saturn with his telescope, and his telescope was only about 3 inches in diameter. So he wasn't able to say resolve the rings with this level of clarity. Here you can see the legendary Cassini division, which is one of the many bands and gaps in Saturn's rings caused by orbital resonances. But what he wrote is that Saturn has ears. So his telescope was just crude enough where he could see that it wasn't a sphere, but Saturn had these kind of ear-like shapes. Remember that before Galileo, people thought of these planets as like the gods, right? So to see Saturn having these little ears, well, whatever, they certainly weren't perfect spheres, right, Daniel? Because you mentioned that earlier. So this meant these were more complex structures than what had been discovered before. Now, the next observation cost Galileo his eyesight. Never point your telescope at the sun. That's rule number 1, at least not without a trained professional. I actually can point my telescope at the sun because I have something called a white light solar filter. I just happened to notice that my white light solar filter was sitting here. I can take one of these 8-inch telescopes and stare at the sun, and I use this. It's a filter that lets in, I think, 1/100,000th of the sun's light. It looks like tinfoil, but it lets in a microscopic fraction of the sun's light, and that allows you to safely observe the surface of the sun. Even with a 3-inch diameter, have you ever taken a magnifying glass and then set like a little leaf on fire by concentrating sunlight? That's
much
how,
like a laser.
yeah, that's what a telescope does. It uses a lens. So you're basically doing that to your eyeball when you look at the sun through a telescope. Not a very good idea, you know. Hold on, guys. I have to put, now that I did show and tell, I wanted to carefully put that away so that I don't end up like Galileo. Okay. All right. So could you imagine staring at the sun for the first time and seeing sunspots? Like the Egyptians, the Mesopotamians, they sort of worship the sun as Ra. He's like your energy god, right? To stare up at the sun and see that it's covered in disease spots would probably be like one hell of a mind twist, right? Of all the things, the sun should be perfect. And to see these blemishes on the sun meant the solar system was this freaky, gnarly place that no one was quite ready for yet. Of all of his observations, however, the phases of Venus were probably the most damning. When Galileo observed Venus, and Venus is one of the few planets that does this. I think Mercury would too, but it's harder to observe. Because Venus is interior to our orbit, we actually see it go through a full set of phases, just like the moon does. Most importantly, including full phases and gibbous phases. Now, this might not be seeming significant, but let's go back and let's look at that geocentric solar system just one more time. In particular, I want to show you the picture that I found, a crappy picture of the Ptolemaic version. It's just a cheap ass cartoon, but it still illustrates a very important point. This is something like the solar system as Ptolemy designed it, where he had all of these extra epicycles to perfect the observations of the planets. You'll notice that some planets have an epicycle which orbits on a primary circle, and the primary circle or the primary circular orbit was sort of going around Earth. But that Venus and Mercury, their epicycles are stuck to a line which connects Earth to the sun. And unless you've spent time observing Venus and Mercury, this might not make sense to you. So let me explain why Ptolemy had to do this. If you want to observe Venus, the rule of thumb that astronomers have for Venus is that Venus is the first star that you see at night or the last star that you see in the morning. Venus is brighter than any other star or planet, even brighter than Jupiter. And usually what happens is when you see Venus, usually you'll see it when it's in the west, just after sunset. So the sun will set, and then the very first star you see will be this really bright ass star, and it's usually somewhere close to the western horizon. Now, if after you see Venus after sunset, remember that the sky is rotating west, so you'll see sort of Venus set a few hours after that. But if you go out the next night and you look for Venus again, you'll notice that the next time it's a little bit higher in the sky. And if you go out to sunset a night after that, it gets even higher in the sky. And it keeps getting higher and higher in the sky each night until it gets to some maximum displacement. Usually it never gets above 40 degrees above the horizon. You'll never see it like over your head or something like that. And this would be called, when it gets highest above the western horizon, I think this is called greatest eastern elongation. I hope that makes sense that it's called greatest eastern elongation, even though it's in the west, right? Does that make sense to anyone, why it's greatest eastern? Because counterclockwise is east across the sky, right? So spinning back towards the west is your greatest eastern elongation. And then if you go out that night or the next night after greatest eastern elongation, you start seeing Venus night by night going the other direction. It goes lower and lower and lower. And then there comes a day where Venus is kind of on your horizon, and then boop, it's gone. And you don't see it for, I don't know, a month or two. And then after a couple of months, when you've almost forgotten about it, one day you get up really early before dawn and you're going out and looking east, and boop, there's Venus. And it does the whole thing again, but now in the east, right? Night after night, it climbs higher in the sky. It gets to greatest western elongation, and then it comes back down again. In other words, Venus is always chasing the sun, but from both directions, right? So look what they did to reflect those observations. When Venus is on the horizon, let me get my annotate tool here. You're seeing it really close to the sun, right? But now, watch this. Greatest eastern elongation would be like when Venus is over there, right? And greatest western elongation would be when Venus is over there. That's when it will be farthest away from the sun. Does that sort of make sense to anyone? You might have to think about that for a minute. Okay. Now, you're supposed to know your phases of the moon. Let me put some Venuses down and you tell me what phase it should have. Venus is kind of yellow. if Venus is here, well, no, sorry, let me undo that. Let me get a circle tool. What phase should Venus have if it's right there?
That'd be the new phase.
Because it's between Earth and the sun.
Yeah.
What phase would it have here?
The full.
No, full is when the moon is on the other
Yeah.
side, right? It's still new, Josh.
Yeah.
Both of these are new because both of those are between the sun and Earth.
System breaks.
Yeah, but it's not the system breaks. It's that these are new phases just by the geometry of light and shadow, right? Because the sunlight's coming from the sun to Venus. How about the phase over here? Now be careful because I know what you're gonna say. If I'm gonna trick you, when the moon is here, that's first quarter. But look at
Yeah.
the geometry between Earth, Venus, and the sun. It's actually not a 90-degree angle, is it?
No.
What
It's
phase
like
would that?
like either a crescent or a gibbous or something.
No. Gibbous is over here,
I'll give it. Okay. So
right?
now it would be a crescent.
Right. So in other words, if the Ptolemaic solar system was true, if it was real, then you should
Yeah.
only be able to see Venus in two phases. It should be new when it's here, or it should be crescent when it's there or there.
But
It should-
Galileo saw a full Venus.
Which is kind of hard to understand unless Venus is on the other side of the sun, right?
Yeah.
So it's basically like he was actually watching Venus go the fuck around the sun. Like there wasn't even any doubt in his damned mind, right? Now pretend you're Galileo and you know this because you're not a dum-dum, right? You're so frustrated because you've actually observed Venus going around the sun, but do you see how that took us a couple of moments to sort of figure out? And we already believe that I think most of us believe the Earth goes around the sun, right? But so I kind of already had you guys in my pocket, but we still had to kind of work through the geometry of that. Now imagine you're Galileo in 1600 and everyone believes Earth is the center of the universe. That would probably be pretty difficult to convince people, right? So here's what Galileo decides to do. Very clever of him. He wrote a book, and let's see if we can find the front page of his first folio. Dialogue concerning the two chief world systems. Okay. Now, back in the day, in fact, up to like the early 1900s, people who wrote scientific treatises would always publish them in Latin. And that's for a couple of historical reasons. The Holy Roman Church was a political institution that spanned Europe. And because everyone conducted masses in Latin, then Latin was kind of a universal language, almost the way English kind of is taken over today like that. So it was the safest language to publish in, which other people, it would ensure maximum readability. But Galileo did not publish this in Latin. He published it in common Italian, like the language that everybody in his neighborhood spoke. This would be the equivalent of publishing a science paper in Nature today with LOLs and LOLs and emoji cons and stuff, you know? Like it would be considered really weird and even uncouth. And in this work, Dialogue Concerning the Two Chief World Systems, let me find a better picture here. I think here's one of the covers of the first edition. Okay, so he not only does he publish it in Italian, but he does it in the form of a play, like a fictional play, where there are three philosophers. So there's the Aristotelian philosopher he names Simplicio, right? And that's basically Italian for dumbass, okay? Simplicio. And then there's Sagredo and then Salviati. Salviati is sort of like the wise Copernican philosopher. You can see he's got some tools. And this guy is in the middle and he keeps bouncing back and forth between the two as they have a discussion. So the dialogues would have gone something like this. Simplicio will say to this middle guy, did you know that Venus always orbits Earth on a line connecting Earth and the sun? And that guy will say, oh, that's very interesting. I guess that explains the observations. And then, Sagredo or Salviati will come along and say, yeah, but if you actually ever observed it with a telescope, dumbass, because I did that, I built one, and I watched Venus go through a full set of phases, which is kind of hard to explain if what that guy said is true. And then the guy in the middle goes, oh yeah, actually, I like what he said better, right? So, and by doing that, he sort of explained his observations and his reasoning for the Copernican solar system to everyday people. And he taught this to his students. Unfortunately, the Holy Roman Church, as I mentioned in my previous lectures, had based a lot of their theology on the logic of Aristotle. And Aristotle came up with some clever ideas. Like, have you ever heard of the Aristotelian syllogism? Like, Aristotle was the first person to write, if A implies B, and if B implies C, then A implies C. Kind of freaking profound if you're the first person to ever think that up. That is known as a syllogism. It's the basis of most logic and even mathematics and computer science, right? It's like substitution of variables or something. If you're starting to use these Aristotelian syllogisms as part of your reasoning for the existence of God, then to call Aristotle a simplicio is almost sort of like calling the Pope simplicio, because you're saying
I'm sure that went over real well if the Roman Catholic Church, the Roman Church there was like, you're basically calling him a dumbass.
Right.
It's like,
and
oh boy.
the history of this has been well studied. It's very complex. It's much more complex than I'm even making out, but I'm just giving you the broad strokes. What is certainly true is that eventually some cardinals got upset about his book and they began complaining to the Pope about it. So they had 2 inquisitions in which Galileo was called in front. And now I want to keep you guys in the right framework here. These popes, these bishops and cardinals, they were not nice people. They were a vicious, bloodthirsty band of heretics that had learned torture from the Romans and were not above crucifying people and pouring lead down your throat and doing all these other nasty things, which they did. They burned Giordano Bruno at the stake for also believing in the Copernican solar system. So in the first Inquisition of Galileo, and Galileo would have been a famous person that might have been a little difficult to persecute, they call him in front of a small group of cardinals and they say, Mr. Galileo, we understand that you've been teaching this heretical doctrine about the sun being the center of the universe, and we cannot allow this. It's very bad for Aristotelian philosophy, so stop. And he said, all right, you got me. I'll go back. I'll stop. But of course, he went right back to his town in Italy and he began teaching the Copernican solar system again. Then they called him for the second Inquisition, where he had to stand in front of all the cardinals and the Pope and the bishops. And they said, maybe we didn't make ourselves clear, Mr. Galileo. We are going to kill you if you continue to teach the Copernican solar system. And they made him recant in front of the entire body of cardinals, right? They made him claim that the earth did not move. Now, supposedly, some people have this legend where he whispered under his breath, and yet it does move, but I don't think he would have done that, because people don't think he would have done that because it would have been much too risky. They spared his life, but they did imprison him under house arrest, where he died old, broke, and blind from staring at the sun. A cautionary tale of what a future in science could get any of you. Okay, so actually, science is a pretty safe discipline to go into, and it usually leads to higher paying jobs. So I really shouldn't make jokes like that. But anyways, it didn't work out so well for Galileo. Maybe it'll work out better for you. Galileo was a contemporary of Kepler. And before I forget to mention this, Galileo at one point wrote a letter to Kepler and said, hey, I built a telescope, Kepler, and I watched some moons go around Jupiter. That's pretty cool, right? Like +1 for the Copernican solar system. And he knew that Kepler was also a famous scientist who liked the Copernican solar system. Kepler designed and built his own telescope. And he wrote to Galileo and he said, why don't we see if p² = a³ will work for the moons of Jupiter? So Galileo went out and did this, right? Galileo went out, and let's look at his observations here. this is how he might have done it. He could wait until the moon gets to greatest elongation. And if you think about it, that would kind of be like the orbital radius A, right? Because that's what the orbital radius looks like. So he would measure the angular displacement of the moon from Jupiter, and then he would time its period, and he would go about and see if p squared was proportional to a cubed. And somehow when he tried Kepler's version, it didn't work. It didn't work, of course, because gravity is connected to the period and the distance, but neither Kepler nor Galileo had that concept available to them. That would take Isaac Newton to supply it. So when Galileo tried p squared equals a cubed and it didn't work, he actually lost some respect for Kepler and his laws of planetary motion. So it's sort of an unfortunate, he's like, this guy doesn't even, his p squared equals a cubed doesn't even work. Very unfortunate. And that brings us around to the thing that I'd like to do with the rest of our lecture today, the last half an hour that I have. It took another great scientist who came 100 years after both of them to be able to put all of these little pieces together and sort of bring them together into a coherent philosophy that basically began to define what is now modern physics. All of these guys made such important discoveries, and they were all pieces of this big jigsaw puzzle or tapestry. And actually not too long, if you think about it, Isaac Newton's birthday is what, a year or so after the death of Galileo, right? So he's like the very next generation of scientists, Isaac Newton. He put all of these little segments together, and he came up with a cohesive idea about the orbits of planets, forces, and he in particular used this to discover the law of gravitation, which is what we really need. We need to understand some facts and some ideas about, well, facts. We need to understand some theories about gravity so that we can understand how our solar system works. So let's make a gentle, not so gentle transition from chapter 3 in our books, which is the history of astronomy, into chapter 4, which is Newtonian mechanics. I'm erasing all this, okay? Okay. So chapter 4 in our textbook is what you might call Newtonian mechanics. It's exploring some of the concepts that were developed by Sir Isaac Newton. Sir Isaac Newton was an English Enlightenment. I guess it would be just safe to call him a physicist, although he made contributions to some other theory fields, most of them which could be considered under physics. Some people call him the greatest. Oh yeah, mathematician. If you invent calculus, I guess you get to be called a mathematician, right, Josh?
Yeah.
Okay. By the way, do you know how old he was when he invented calculus?
Didn't you say he was like, I don't know, 16 or something?
21. 21 when he invented calculus. Yeah. And he invented it to
That's insane.
Yeah, right? That
That's
nuts?
insane.
By the way, he was not like a genius A+ student. When he was in Trinity College, he was considered to be like a subpar, lackluster C+ student. It wasn't until the bubonic plague struck London, and just like our modern history of what's going on with the coronavirus pandemic, all of the students had to flee London because they thought it was dirty city air causing the bubonic plague. It was actually mosquitoes transmitting it from rats to humans. So they all fled the countryside and they all moved home to quarantine. And he brought back to his house all of his textbooks, which were probably dialogue concerning the two chief world systems, and probably Copernicus's De Revolutionibus, and probably Kepler's Harmonious Mundi. And he just sat around with nothing better to do. Unfortunately, there was no Nintendo and no Netflix, right? So what else are you going to do? You're going to read Harmonices Mundi. That's your Netflix. and he started thinking some deep thoughts, okay? Of his deep thoughts, which were eventually all published in the legendary Principia Mathematica, okay? There are 2 or 3 key concepts that I would like us to develop as part of our studying of Newtonian mechanics. So Isaac Newton sort of, how do I explain this? He was basically responsible for defining the concept or the hard definition of a force, okay? And he basically put it on firm mathematical footing. A force, in a touchy-feely sense, is a push or a pull, but he described it in great detail. And he also sort of came up with 2 different sets of laws. He came up with the 3 laws of motion. Sorry, let me try this. I'm a little squished here. His 3 laws of motion. And he also discovered the universal law of gravitation. These 2 laws were both published in the Principia Mathematica. That's his legendary book. And the book is now considered even more than a book about physics. It's mathematic. Sorry, lost an A. It's considered to be more than just a work of physics. It's now considered to almost be like a work of Western philosophy. These laws of motion and the law of gravitation were both published in Principia Mathematica, but they are, even though they can be combined in complex ways, they are sort of separate concepts. The 3 laws of motion explain how an object moves when subject to an arbitrary force. In other words, you kick the soccer ball, right? And if you know how hard you kick the soccer ball, Isaac Newton will tell you how far it'll travel before it stops or comes to rest or something like that, right? Then there's his law of gravitation, which is what we would call in physics a fundamental force. Fundamental forces are really cool because they're basically a mystery of nature. Fundamental forces are a mystery of nature. We know that they exist, right? I mean, hell, you drop a little ping pong ball and there it goes. The magic of gravity takes over. But somehow gravity is a force that's built into the machinery of the universe itself. It's sort of just been there from the beginning of time or something like that. It's always been a part of the universe. Sometimes I like to make a chessboard analogy about the universe, right? The squares of the checkerboard, they're like space and time. There's like sort of a 4-dimensional space-time connection. And then the pieces on the chessboard, they're kind of like the matter or the energy of the universe. You could think of them as galaxies or stars or photons or something like that. The fundamental forces are the rules which govern how mass and energy interact with space and time, right? If a king can only move 1 square in any direction, that's a sort of fundamental rule that's baked into chess. And gravity is a fundamental rule that's baked into how the universe works. And while there are many forces, the force of friction or other things, it seems to be that there are sort of these fundamental forces that are difficult to resolve into smaller components, although we've been trying. When I was younger, scientists studied the 4 forces of nature, which included gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These were called the 4 forces of nature, and the relationship between them was unknown. Since I was a student, now in 2022, people through the study of subnuclear particles and particle smashers like the Large Hadron Collider, we believe we are getting close to an understanding of how 2, 3, and 4 are related. And today, the dominant framework that explains connections between these 3 is what's called the standard model of physics. And the standard model of physics are a set of rules and laws that regulate how particles like quarks and gluons interact with each other. Some people think that all 4 forces might be part of a single kind of Yoda-like force, the force, right? It's one mathematical equation which would explain the evolution of all the particles in the universe, from the Big Bang all the way to the Big Crunch or the heat death, whichever you subscribe to. And that would be cool. That would be like, you know, some Star Wars shit right there. But we're not quite there yet. We haven't actually figured out how these 4 things are connected to each other. In particular, it's gravity that still ends up being the most mysterious, despite it being the first one discovered by Isaac Newton. And one of the reasons for this, my friends, is that it turns out that gravity is a weak ass force. It's so wimpy, in fact, it's so subtle that one does not even notice gravity exists until you literally build up a giant planet's worth of matter. And only then, with a clump this massive, do you actually start to notice, hey, there are things sticking to this thing, right? That's what makes it so difficult to study in particle smashers. Because let's face it, there should be gravity between these ball bearings here. They are particles of mass. And yet, one cannot feel that force of gravity. It's so microscopic that it's almost zero, right? So if you shrink this down to the world of electrons and protons, gravity almost ceases to exist. I mean, it doesn't cease to exist, it's still there, but it's so weak that it's hard to test it because these other forces are so much more powerful at those microscopic scales. All right, well, I'm getting ahead of myself as usual here. Why don't we see if we can focus on this today? And then when we meet in person next week, we'll begin the law of gravitation. That's when things get computationally intensive. And that's when calculators will be necessary. Please, for the love of God, I want to say this to all of my students. I hope you made it this far in the recording if you're watching later. Please bring this with you to class, okay? Because we're going to start doing some crunchy stuff, a lot of number punching. And if we're all there in the same room, all right, one of the cool things about us all being in the same room is I can kind of walk around and make sure you're actually getting it right. And that's a service I can provide to you, and I would like to do that. So have these, okay?
I have a question.
Sure.
When you said that gravity is like a really wimpy force, do you mean like the fact that it's only here on Earth and on space, it's like a whole 0G type of thing?
No, gravity continues to exist in space as well. It's just gravity gets weaker the farther you get from massive objects.
All right.
Gravity still exists, you know, even if you're in outer space, that 0G thing is a little bit of an illusion. Well, it depends if you mean microgravity, the gravity you experience in the orbit of Earth. If you do get far enough away from Earth, you're actually in the same predicament because you're still orbiting the sun. It's actually quite difficult to find a place in the universe where you're not experiencing gravitational forces. Well, you can actually do it, but you'd have to get really far away from a galaxy into one of those big bubbles or voids where we think there's very little matter. I don't know if you
Oh,
get
all right. Thanks.
so
Yeah,
Lionel.
I watched a pretty interesting video last night that left me really shook.
Oh, was it a science video or?
It was an astronomy. It was like somebody was counting down like the end of like the universe, but they were going like in fives until it got to like trillions of years, and it showed like this huge process, and it left me shook. I was like,
It's the universe is a pretty freaky, weird place, my friend. There's a lot to learn. This class is your first journey through that, and I'm excited to take you on it. Let's get back to business here, and we can talk more about that stuff later, Lionel, especially in my 1020 class. Okay, so before I give you his laws of motion, we have to do some really basic baby physics stuff. And we have to just come up with a few concepts that might be necessary. First of all, in physics, we're going to be using a new set of units. Units are often the key to understanding physical quantities, okay? So let's talk about new units for physics, okay? And they are known as the MKS system. And they're basically sort of like your standard metric units. There are many different metric units. The basic quantities that we will be considering are either length or distance. I don't want you to think that's divided by length or distance. And then there's mass. And then there's time. In your first journey through physics, most complex concepts like forces and energies can be resolved into combinations of length, mass, and time. And the standard units that we would like to use for now to measure these quantities are the meter, the kilogram, and the second. These are the standard units that we'll be using in chapter 4 to measure things like forces and gravity. And because they begin with M and K and S, they're known as the MKS system of units. Most physics students will start off learning quantities in this system and then proceed to others as they get more advanced. We are going to need to do conversions, and I can help supply a couple of useful conversions. 1 kilometer is equal to 1,000 meters. That's a conversion factor that will come up in our class all the time. We might occasionally need some other ones too. A meter equals 100 centimeters is also useful. But this one is really, really useful because we're constantly having to convert from planet radii into meters. For the kilogram, every now and then it'll be useful to know that a kilogram is 1,000 grams. These are all metric units, but we're showing you how to convert back to MKS. And then for seconds, I find it very helpful to be able to write down the number of seconds in 1 year. 1 year is equal to 3.15 times 10 to the 7 seconds. These are conversions that I've learned over time are really useful to have in your back pocket for this class. I'd like to erase. Okay. Next up, a couple of quick definitions, and then in 8 minutes or so, we'll break for the day. Okay, so let's see here. Let's talk about the difference between speed versus velocity. Josh is going to have to forgive me because he knows the difference between these two things, having studied physics in a few of his courses and in my other course. Okay, we'll keep it quick and dirty. Speed tells you how fast something is moving, but in sort of one direction only. Speed is one-dimensional motion, and its units are meters per second in the MKS system. Probably the most legendary equation is distance equals speed times time. And by the way, speed is also rate, okay? Same thing. Oftentimes, it's easy to talk about just how fast you are traveling without needing to reference anything else. For instance, I could tell you that, come Monday morning when I'm rushing to class, that the professor may need to drive at 90 miles an hour from downtown Providence to CCRI in his van. Now, it may not exactly be a straight shot, but we imagine in our minds the professor traveling from home to CCRI in a straight line. That's a good example of a speed, because you're just thinking, how fast am I traveling? But it turns out that sometimes you want to talk about the direction of motion in a two-dimensional sense. And that's where velocities come in, because they're a slightly different concept. And if you don't pay close attention to this, you end up getting burned over time. A velocity is a combination of a speed plus a direction. And the direction can be in a 2D sense, like you see here. A boat travels 100 knots per hour, 45 degrees east of north. It could also be in a three-dimensional direction as well. And so we define a velocity as a speed plus a direction. And that makes it, well, what do we call it? A vector in mathematics, right? A velocity is either 2D or even 3D motion. If you change either speed or keep your speed constant and change direction, you get, and wait for it, next big topic, acceleration. Now, let's also make note here that velocity has the same units as speed, meters per second. The direction just adds a little bit of extra information. Acceleration does not have the same units as velocity or speed. And acceleration is defined as a change in velocity with respect to time. Here I'm using these little delta symbols from mathematics. V2 minus V1 over T2 minus T1. So if I wanted to define in a cheap sense an acceleration, I could say an acceleration is basically a change in velocity. Now, people usually say a change in velocity with respect to time, but that almost seems semantic because almost everything takes time, right? It's a change in velocity. And probably one of the most legendary accelerations is the one that Galileo discovered. he discovered the local acceleration of Earth's gravity little g. Now, famously, when Galileo discovered the local acceleration of gravity, I wish I hadn't, let's see here. I got rid of my lecture notes. I wish I hadn't done that. Oops. Let's see if I have that in the history of astronomy here. That'd be cool. Oh yeah, here we go. So this is the device that Galileo used to do it. And like many of Galileo's most legendary works, function F587, Galileo was attempting to refute one of the laws of physics that Aristotle had written in his famous book of physics. Aristotle was kind of the first person to write a book of physics, and it was called, wait for it, physics, okay? In fact, we kind of owe the concept of physics to Aristotle. This is why he was cool. He was the first person who thought to write a book and try to explain basic things that were happening in the world, like why does an arrow fly through an air? Why does a stone come to rest if you roll it along the ground? And in a sense, Aristotle got this whole thing going. It's just that a lot of his ideas were buggy, okay? One of the things that Aristotle claimed is that if you had two stones, a massive stone and a light stone, I think he called them heavy and light, he claimed that a heavy stone would fall to Earth faster than a light stone. Now, if you're Galileo and you've discovered that Aristotle was full of shit almost 90% of the time, you start wondering, is that actually true? Or is this just another crazy thing that he just sort of made up without testing it? Galileo was a testing type of person. So he decided to build a device that would actually test this theory. And he designed this beautiful artificer here. It's his inclined plane. And Galileo famously placed spheres of different densities. He had one made of wood, he had one made of stone, he had one made of metal, and he rolled them all down the inclined plane. Now, because he didn't have a stopwatch or something fancy like that, do you guys see these little bells here? That's what he used to time the rate that they fell to Earth. So as the spheres triggered these levers, they'd make a little ding on the bike bell there, and he could time the rate at which they were falling by measuring the cadence or the frequency with which the bells were increasing, right? So as it goes ding, 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 he can hear the balls speed up as they're rolling down. Of course, the point of the inclined plane is if you just dropped this from top to bottom, it would move so fast it would be difficult to get a good measurement. The plane slows the rate at which they fall so that you can make very careful measurements. And basically, let's take a look at what he discovered. We could do a much different version of the experiment today because we actually have devices like laser gates, which can very carefully measure velocities when things pass through them. And what Galileo discovered and what we would discover is that if you drop a ball from the top of the building, it will start to speed up by magic. You can tell that there's an acceleration at work because when you're holding the ball in your hand, its velocity is 0 at time 0. And when you remove your hand, the ball immediately begins to fall. After 1 second, it travels at 10 meters per second. After 2 seconds, it will travel at 20 meters per second. And if you neglect air friction, it will keep increasing its velocity each second. That is an acceleration. For one of our last acts of the day, we will explore the units of acceleration by means of trying this equation here, okay? So let's focus for just a moment on little g. Let's find the units of acceleration. And let's calculate little g using the formula change in velocity over change in time. And I'm going to use those two data points that we had a moment ago. We'll have t and v At time 1, we're traveling at 10 meters per second. And at 2 seconds, we're traveling at 20 meters per second, right? And so I'll plug these into the equation. We have 20, here I'll use blue for units, meters per second minus 10 meters per second, right? Over 2 seconds minus 1 second. 20 minus 10 is 10 meters per second. 2 minus 1 is 1 second. And 10 divided by 1 gives us 10. Now, Josh knows, and Ethan knows. Daniel, do you know what the units should be here? Daniel or Cole?
Should it be meters because the seconds would cancel out? I mean,
I was hoping you'd say that, Daniel, because it's wrong. Okay, that's what I was hoping you would say. All right, Daniel, we got to talk about fractions for a second. Okay.
Okay.
Fractions within fractions are tricky. 3 out of 2 people are bad at fractions. Mateo, go ahead. Give me a shot.
Isn't it meters per second squared?
That's right. But Mateo, even that is correct. And that's the whole point that I wanted to make. That little g is 10 meters per second squared. And by the way, let's say that these are units of acceleration. But Mateo, even though you knew that, we have to have this talk, buddy, because I've learned the hard way. In the next week, when we're going to be doing some much more mathematically crunchy things together. And sometimes we're going to have to balance our units with fractions within fractions. So let's come up with a quick rule here. I want to divide 2 fractions here. A divided by B over C divided by D. So notice I've got a fraction in the top, in the numerator, and another fraction in the denominator. And I want to reduce it to a single fraction with just letters on top and letters on bottom. And the colors that I've chosen suggest to you how things work. The top of the top fraction will end up on the top. The bottom of the top fraction will end up on the bottom. The top of the bottom fraction stays on the bottom. And the bottom of the bottom fraction flips back up to the top. That's a little rule that you can use to help you. So Daniel, do you see what your mistake was? This is a per second on top. That is the bottom of the top fraction, right? So that second drops to the bottom. But this is actually kind of like seconds over 1. That's like letter C here, right? So when you have a meter per second, it's a meter per second, which is a meter per second squared. It looks at first like they cancel out until you realize, wait a minute, there's like a complex mixture of fractions going on there. And I wanted to make that very clear. This rule might be helpful to you guys, not only in my class, but in other classes as well. So commit it to memory if you can. Okay. I guess that's all I have time for today. Let's talk Turkey. Today, in theory, we should be doing homework 4. And homework 4 is based on the Newton mechanics stuff, but we are just not there yet. We have more lectures that we need to do. So here's my suggestion to the class. Why don't we let ourselves off the hook on homework for this week? And that will actually serve a number of different functions. 1, it lets us finish early today, which I'm sure everybody loves. 2, I'm thinking about night class people. Who's in the night class? Anyone? Or you all? Josh, we're going to eventually do it the way we did our other night class in 1020, where we have office hours before class.
Okay.
But
Is office hours next week or?
I'm thinking no. I'm thinking next week for our first week back together, we'll meet at 6 p.m.
Okay.
I was gonna have us meet at 4 p.m. for office hours, but we're just not there yet. The next homework, like we need more training on like gravity
Yeah.
and stuff. Because that was a tough one. So,
Yeah, it's a lot.
so for the daytimers, here's how I think this is gonna work. If you have lab on Monday, and this is gonna suck a little bit, so steel your nerves for this. We're gonna do lecture on Monday, and then those who are in section 001, we are gonna do lab, and then we're gonna do homework right after it. And if you don't like that, ask yourself, when else are we going to do homework? And how would I get everyone available at that time? You'll quickly realize there's no good answer to that question. Hopefully, most of you can make it. If not, we'll come up with a workaround. Wednesday people will do lab and then homework. It kind of sucks, but I did it last semester and it was fine, honestly. It wasn't, we just moved quick. And that's because the lab room is very small. The lab room can only hold, I think, 12 to 13 people at a time, right? Maybe 14 at tops. And I think your
Yeah.
class has 14 sections. What's the current list of students? I don't know if anyone's dropped out, but currently my list shows for the daytime, 13 in section 1 and 13 in section 2. So there's no way I think I can fit everyone. I mean, I'm contemplating doing it. If I could squeeze everyone into that lab room, but 26 people, I just don't think that Ethan, you know how small that lab room is, right?
Yeah, the one class we had on Friday barely fit in there. It was like just enough, and I don't know how many kids were in that class.
Yeah. No, we're asking to get the Rona, just doing that. All right, just even thinking about it. It's not even that, just aren't enough seats, right? So, okay, so that's how it's going to be. The night people, it turns out that doing this thing remote actually had some advantages, right? That's actually the sad thing. We all probably got used to this, and going back in person is going to take a little more time. Hopefully there are things that we will gain from it. Hopefully, but we're all doing this together, okay? So night students, we will be doing office hours before class, but we won't do it this one time. But however, the daytime students, we will be doing homework next week. One of the things about the night classes, they always end up being, you kind of have a lecture and then I can't even, just trust me, okay? I'm not trying to waste anyone's time. I think you guys know that by now, right? I'm doing
I just
things.
have a quick question.
Sure, Nina.
So I'm in 002. So on Monday, will it still be lecture from like 11:30 to 12:45 and then lab and then Wednesday class and homework?
All right, let's make this very clear. So this is just for daytime students. I'm going to erase this here. Hold on. I want to make this real clear, Nina, so that there's no.
Yeah, sorry, I just got a little bit confused with the sections.
And I'm glad you asked this question, because if you got confused, others will too. Everybody in the daytime class comes to the same lectures, okay? So for the day class, we have lecture on, sorry, this is Monday and this is Wednesday, right? Everybody has lecture from 11:30 to 1 p.m. And that's everybody, okay? And that's because the lecture room is really big. So all students, whether you're in, okay. When I say all students, I mean 001 and 002. The night class meets Monday night. So you have to be there both days, Nina, no matter what section you're in. But if you're in section if you're in section 002, Nina, that means on Monday at 1 p.m. in theory, you're free.
Okay.
So here, this will be 002 lab and somehow plus homework. And here, this will be 001 lab plus homework. And that will be in the lab room in room 2050. You see what I mean?
Okay, so I only need to stay after on Wednesdays.
Exactly. And hopefully that works for you.
Okay, I'm going to take a picture of this. So thank you so much.
You're
that
welcome.
Really makes it more clear.
Yeah. Just make sure that part was clear, that all students have to be there for that, right? Okay.
Okay, thank you.
Yep. And the night class, by the way, the plan for the night class, and some of you will be watching this later, is normally we do our homework in office hours from 4 p.m. to 6 p.m. Yeah, I know some of you are going to bitch about that, but we're going to have a talk about why that's the best of many bad options. Okay.
Honestly, I thought it was pretty good. It's like, okay, you get your mind into it, and then it's like, okay,
Now
just
it's talking
grind
about-
out the lecture, and then, yeah,
It actually kind of has a certain flow to it that's good, right?
yeah, you like
remember,
you do
guys-
the homework, you get into the topic. It's like, okay, in our class last semester is like, all right, we didn't do this in class yet, but we're gonna do it. We're gonna do it today. So here's the topic that we're gonna talk about today. You get your mind into it. It went pretty smoothly.
It actually kind of works out decent like that. And so a Monday night class just meets 1 day a week. So it's all of this packed into one night: homework, lecture, and lab. Now, I want you guys to know something about me. There is no bigger slacker than me. There is no one more willing to shirk a responsibility, to cut a corner, or to make things just a little more efficient and a little more fun and a little less work. So if I'm constructing the schedule, you need to know that I've designed it with the minimum amount of pain, bullshit, and time necessary to get our job done. Okay, so just follow the Pied Piper here, okay? And it's gonna work out fine. And Josh has seen that as well. Okay, so I'm glad we had that talk. And I'm glad I get to let you out a little bit early today. That's a little treat that I can give you. And I am looking forward to seeing some of you people like Nina the troll, who has been here with us, but hiding in the background. And I'll meet some of the rest of you next week.
Yeah,
So
my camera's been like weird.
that's okay.
Why it used to work, and then my computer's kind of old, so yeah, it's just gotten weird. It's like it's a MacBook, so the camera's also like very fuzzy, and for some reason, like whenever I do it, it's like inverted now.
Oh, weird. Yeah, you can change some of those settings, but
Speaking of weird, are we gonna just be getting right into the regular class times as 11:30 to 2:30 as everybody expected within the same class session in a different classroom?
well, we're going to be following the official CCRI schedule. Class will begin at 11:30.
Like that's already been established. Stop beating around the point. Are you getting to two different classrooms, or is it one classroom for your class session?
There's a classroom for the lecture.
And the classroom. Okay, so you're saying there's two classrooms.
There's two classrooms. Yeah, and to add to this, which I did here, so you'll see I have room 2050 for both lab rooms. That's night campus 2050. And the lecture room, I believe, is room 6062 for the lectures. So that's something I can add, Preston. 6062. Those are the time slots. Those are the rooms. You can also see that on your schedule under My CCRI.
The office hours, they're still in near your office, right?
Well, for the daytime, we're already in the lab room, so it's most efficient to just do them there. But for the night class, I do have in fact, I should say that the night class, the problem is I'm forgetting the conference room number. I think it's 2201. So
yeah,
this,
it's like
the office hours is room 2201, although we're not having it this week. The lecture is now in the same room as the daytime. It's room 6062, and the lab is the same as the lab classroom 2050. So that ought to help night students watching this later. But we will be doing this next week. Next week we will meet here at 6, just the first time. And that's just a night class specific thing for Josh's class, okay? So after next week, we'll have office hours. And Josh, I'll have to do my song and dance and make my pitch to the night class. And by the way, night class, if you're watching later, here's my pitch in a nutshell. Do you want to do these freaking homeworks by yourself, the way you're supposed to? Or do you want to do them with me? And if you want to do them with me and you're only coming to class once a week, when do you want to do them? Tuesday at 9 p.m., Wednesday at 3 a.m., or do you want to do it just before class? You either have two options: do it on your own or do it just before class when you realize you didn't do it. Okay, so that's what I think
like
is
an ultimatum.
well, it is. I mean, I don't know any other classes that don't have homework. I am actually trying to make it so that you can do all your work with me and not have to take this stuff home with you. which if you think about it is great because it's all kind of just in the can, right? You just show up, watch the show, and then you're cool. Like it's low stress. That's what I want it to be. I want it to be as minimum stress.
Yeah, I appreciate that a ton. You have no idea, because I'm gonna be real honest. If it wasn't for you helping us do the homework and doing it with us, I would have been a complete 100% fail.
And you know what, Lionel? You know what I learned over time? It wouldn't have even been your fault. It's that if you haven't had a science class before, it's hard to even know what format you're supposed to do, what the rules are, how it's supposed to proceed.
Yeah.
This is your introduction to science to show how it should work. A lot of students have told me that taking this class actually helps them think about many of their other classes in a good way too. So I believe that the things
you learn how to get organized.
a little bit, yeah, and you also kind of have a feeling about what a good homework should look like and stuff. So anyways, who knows? I'm trying my best. In any case, I had fun with you guys today, and I will see you Monday at 11:30. Most likely. All right. maybe 11:32. We'll see. Okay. But very close to 11:30 to within tolerance. Okay.
That's good.
All
So,
right.
Professor, I'm gonna send you that video that I saw last night. If you don't mind, I'm gonna send it to you on the email.
Please do.
so-
I love it. I love it when you guys see cool astro videos or news blurbs and send it to me. Oftentimes that helps keep me informed, and then we can have a cool discussion about it. So please send me that link, Lionel. I would love it. Cole, what are you thinking?
I got you.
Will we be going to like the observatory like as a class, or is that something we have to do on our own time?
So
with you?
here's the deal. I used to make it mandatory for day students to go, but I realized that was such a stress for students who have very tight schedules. Some of them have families and kids they need to take care of, and some of them have night jobs. It just wasn't fair. So what I do is, if you're in the night class, it's already dark out. So for one of the labs, instead of doing a lab, I'm going to actually take them to the telescope. That's one of the cool benefits of being in the night class, Josh. Cole, for the daytime people, I run a public open night, which I'm going to start next week. And anyone, not just my students, but you can bring your dad or your kid brother, or bring your dog if he doesn't bite, and so, the problem is with the weather, it's hard to predict. If you just type in CCRI Observatory, the page that I run shows up. And so Josh, I'm sorry, Cole, forgive me, Cole, rather than force you to come, which might be stressful for someone, I'm giving you an invitation to join me if you would like, and come on one of these Wednesdays. And if you ask Josh, it's a really cool thing to do, Cole. Like, you could come with a friend or your girlfriend or boyfriend or whatever. And if you come, you can just show up at any time between 6 and 9. You can just show up for like an hour, and I'll just show you whatever cool stuff is in the telescope. And it's wicked chill and wicked fun. But I wanted it to be an invitation, not an obligation for daytime students. Does that make sense? But it's, especially if you're in class some Wednesday, if you have a Wednesday night class, you get out around 7 p.m. It's so easy to just stroll right down there and take a peek. And I can tell you guys more about that when we meet in person, okay? I usually post whether it's open or closed day of, because Cole, even a week out, it might say it's going to be clear, but that'll change within a few days. So I'm really only ever sure the day of. So the day of, I say, yes, it's open 6 to 9, or it's canceled tonight. Rule of thumb is it's about 50-50. You get a roughly 50-50 chance. Okay, guys. Thanks for chatting with me. I will see you all next week live in the Rhythm Hive. Okay. So send me those fun email links, and I'm going to catch up on the homeworks. That means this week you only owe me lab 4, but I'm going to catch up. I'm going to grade lab 3, homework 3. I got to catch up on that. I'll grade those, and I'll grade lab 4, and that's where we'll start for next week. So I'll see ya. Peace.
See ya.
Have a good night.